Section 14.2, Properties of Limits. The objectives are to find the limit of a constant function and the identity function, use the properties of limits, find the limit of a polynomial function and radical functions, and use the limit theorem. Now let's first look at the properties of limits, the limit of a constant. For some constant function that we have, f of x equals b, where c is any real number, then the limit as x approaches c for the function f of x is the same thing as the limit as x approaches b, because that's what our function is for this. Now what that means is, let's say that we have this graph right here. So this is your x-axis and this is your y-axis. And we're saying that this equation of the line is f of x equals b, or we could write y equals b. And we're calling this value right here c. Now remember, we said before we're trying to figure out the limit, or your y value, as your x values from the left and the right are approaching this value right here. So if we go along our line this way towards c and this way towards c, notice that my y values are always equal to this y value b, which is why we say the limit of a constant is a constant. So now let's actually just plug some numbers in there to make this a little bit easier to see. So for instance, if I say f of x is equal to 5, that means that this line would be y equals to 5. So for this, if I wanted to find the limit as x approaches any value on my x-axis for this function f of x, I'm always going to get an answer of 5. And the reason I'm always going to get an answer is 5 because I have a horizontal line, so all my y values are going to be equal to a y value of 5. So we can also write this as the limit as x approaches c for 5 is equal to 5. Let's say I pick some numbers instead. So let's do as x approaches 2. So the limit as x approaches 2 of the function y equals 5 would just be equal to a value of, again, 5. And we could keep on doing this because, again, a horizontal line, you're just going to always have a y value of 5 come out for your answer. Now, the limit of x, which we call the identity function, if you recall from our parent graphs. So this is y equals x, or you could say f of x equals x. This is your x-axis and your y-axis. The says that the limit of the identity function x is going to be equal to whatever value it is that you're trying to find for the limit. So if this is c right here, and we're trying to find this value right here, then we would just say, again, the limit as x approaches the c value from the left side and the right side. So this would be the right side and this would be the left side. Notice that on our graph, we would meet at the same place. Where are we meeting at? We're meeting at a y value of c. So let's try some numbers in here instead. Let's make this maybe 5. So the limit as x approaches 5 for the function y equals x, so you can just write x right there, would be equal to a y value of 5. And again, that's called the limit of x. Now, just to look at these really quickly, so if I wanted to do the limit as x approaches 3 of 5, of course this is a constant function, so my answer would just be 5. For the next one, this is the identity function, so the limit as x approaches 3 of x, if you plug 3 in for x, you get 3 out for a y value, so that would be your answer. For the next one, we have the limit as x approaches 0 of negative 8. Again, it's the constant function property, so negative 8, and the limit as x approaches 1/2 of x would be equal to 1/2. So again, those are just properties that you need to know. And I know I can do that for the limit of x as x approaches 3 for x, for this one right here, because 3 is within the domain. So anytime it's in the domain, you can really just, as a quick way, just plug the number in. These that we have right here are all properties of limits. So you can go ahead and read through them. It just states that if you have two functions and you add them together, then you can separate them using addition and find the limit separately of each one, and it will give you the same answer as if you did it all together, which I'll show what that means. And you can read or look through all these, which is also in your book, so I'm going to skip through that. So the limit of a polynomial function, and actually just to go back real quick, let's go ahead and just write down some of what that was. So like if I had, just to show you f plus g, then if you have two functions, let's say f of x is equal to 4 and g of x is equal to x. So then f plus g would be equal to, and I could write x if I want, 4 plus x. And if I did f divided by g, that would be 4 divided by x. If I did f times g, and I guess, yeah, we can write like that, that would be equal to 4x and so on. So those are what the properties are saying. The limit of a polynomial. So if f of x is a polynomial function, then the limit as x approaches c for that function is just c. That means you can plug it into your function, which is really nice. And remember that polynomials don't have variables in the denominator, and they also have whole number exponents. For this first equation that we have right here, this is a on your sheet, or if you don't have a sheet, just write it down. The limit as x approaches -4 for x squared minus 2x plus 3. The way that we would have to solve this is by using all of these properties right here. So if I have part of my function being added or subtracted, then I can separate this by doing each of the limits separately. So the limit as x approaches -4 of x squared, we can also add that to the limit as x approaches -4 of, in this case, let's actually do this minus right here instead. Minus, and make this just a positive 2x. So the minus the limit as x approaches -4 of 2x, and then this would be plus the limit, as x approaches -4 for the value of 3. And then we're not done, because here x squared we can make as x times x, so I can separate that into the limit as x approaches -4 of x, and then it would be multiplied by the limit as x approaches -4 of x, and then minus, and then we can do both of these by multiplication, so I'm going to put it in parentheses, the limit as x approaches -4 of 2 times the limit as x approaches -4 of x plus the limit as x approaches -4 of 3. Now, for this, the reason why we split it up is because this allows us to use our properties of limits, the limit of a constant and the limit of x, to evaluate what this limit would be. So if I look at the first one, remember that the limit of x would just be that number. So right here, for this first one, the limit as x approaches -4 of x would be -4. And we're multiplying it by this limit right here, so that would also be -4. And then we're subtracting it from the limit of a constant would be the constant, so in this case 2. And here we have the limit of x, which would just be times -4. And then the limit of a constant is just that constant, so plus 3. And I can just have to use some algebra in order to simplify this. So -4 times -4 is 16. And then we have minus 2 times -4 would give me -8, and then plus 3. So in your calculator, if you do 16 plus 8 plus 3, you end up with 27, or you can just do it in your head. That means that the limit as x approaches -4 for this function is equal to a value of 27. Now, this would be a lot of work to have to do all of these properties every time. So that's why we said before, I called this an easy limit, because if the value, which I said in the last section 14.1, if this value is defined within the function, then you can just plug it into the equation. You don't have to do all of this work. So I know the domain of x squared minus 2x plus 3 is all real numbers, because I don't have any variables in my denominator, nor do I have any variables underneath a radical, or even root I should say. So in this case, I could have just done the limit as x approaches -4, and I could have plugged in, so x squared minus 2x plus 3, all I had to do really was plug in -4 for x. So this would be -4 squared minus 2 times -4 plus 3, and I get 27. So that's what the whole property is saying, is that instead of having to do what I just did in the blue, you can just go ahead and plug the number in if it's defined for that value. So the next part says the limit of a rational function. Let f of x be a rational function and let c be a real number such that f of c is defined. Then the limit as x approaches c for f of x is equal to f of c. When a rational function is not defined at a number, there are going to be different techniques that must be used to find the limit there if it exists. And different techniques are usually algebraic techniques that you can do. Let me show you an example of this one up here. Let's say we want to find the limit as x approaches 2 for the rational function. Let's do 1 over x. So if I wanted to find, in this case, the limit as x approaches 2, well, because 2 does not make my denominator 0 there, because my domain would be all real numbers except for 0, that means that I can just plug 2 into my equation and this would be my limit. Now, when it's not defined, such as, let's say I had the limit as x approaches 3 for the function x plus 3 over, let's do 2x, no, let's do x minus 3. So if I plug 3 into this equation, notice I would get 3 plus 3 over 3 minus 3, and this value is going to give me 6 over 0. However, notice that I can't divide by 0. So this is what I was saying, that there is going to be some other techniques that we'll do in order to solve and find the limit for this problem. Now, the limit theorem states that if f and g are functions that have limits as x approaches c, then f of x equals g of x for all x values not equal to c, then you can find the limit of the function by just using algebra and simplifying your equation to find out what it would be equal to. And you're saying, what in the world does that mean? So if you look at your example G on your page that I gave you, here we're finding the limit as x approaches -1 for this function. We have x squared minus x minus 6 over x squared minus 9. And I just noticed on the paper that this is actually supposed to be as x approaches 3. On your paper, that's what it says, not -1. So that was an error in my notes here. So if we want to find the limit as x approaches 3 for this function, well, let's try it. So 3 squared minus 3 minus 6 over 3 squared minus 9. Well, notice right here, I get 9 minus 9, which equals 0, but we can't divide by 0. Now, because of that, that means that I can't just plug in 3 to get my answer. I'm going to have to use some other techniques, such as some algebra. If you look at the numerator versus the denominator, one technique is factoring. If I factor this equation, I get x minus 3 times x plus 2 over x minus 3 times x plus 3. So this is what we did when we simplified rational functions. So the x minus 3 and the x minus 3 cancel out to leave me with x plus 2 over x plus 3. Now, this is what the problem is saying for the limit theorem. It's saying that finding the limit of this function, if it's not defined, well, then we can simplify it and find what the limit would be for this function, which we would call g of x, and this one would be called the f of x. If we find the limit for g of x, then it's going to be the same thing as the limit for f of x, and it just gives us another way to solve the problem. So now I can do the limit as x approaches 3 for x plus 2 over x plus 3 by just plugging in 3 into my equation, because it's not going to make my denominator 0 anymore. So 3 plus 2 over 3 plus 3 gives me 5 over 6. So the limit as x approaches 3 for this problem would be 5 over 6. And another thing that I can do is always double check using my graphing calculator. Remember, we showed that you could plug this into your graphing calculator and then look at values as you come very close to 3 from the left and from the right. So I plug this into my y-equals just to show you. Here's what the graph looks like. If I do second trace value, so second trace value of 3, notice that nothing comes up for my y value, and if I go to my table and change my window to auto, and if I look at 3 in my table, notice it's not defined there because I have a hole in my graph, if you remember from when we talked about rational functions and graphing these. So because it canceled completely on my denominator is why I have a hole. If I plug in the other function that we simplified, just to show you, the graph looks the same. The only difference is now, instead of having a hole, we took out that hole so that we could find the value of what it's equal to. And if you look here now, we see we get 0.83, which is really equal to 5/6. So it's just a different way of finding it. Or you could also do second window and go to ask and look at the table values as you come very close to 3. So values very close to 3 from the left side of your equation are going to be values less than 3, so 2.99. And then values from the right of 3, very close to 3, would be like 3.001. And notice that it's coming to the same number, which again is 5/6. And just to even show you, 5 divided by 6 gives you 0.83, repeating. Let's do some more examples of this. Looking at the first one, we want to find the limit as x approaches 4 for the function 6 minus x. For this function, because we don't have anything to worry about for our domain, it's all real numbers, that means I can just go ahead and plug 4 into my function for x and solve. So that's why I call these easy limits. So really my answer is going to be 6 minus 4, which is really equal to a value of 2. So the limit as x approaches 4 for this function is equal to a value of 2. So again, that's an easy limit. So the next one, again, this is another easy limit because -5 is in the domain because it's all real numbers. All I have to do then is plug -5 in for x. So -4 times -5 is equal to 20. So the limit as x approaches -5 for -4x is equal to 20. We keep going. We have the limit as x approaches 1 for the problem, 3x minus 5 to the 4th power. Again, all my domains all real numbers, so if I plug 1 into the equation, I get 3 times 1 minus 5 to the 4th power. And if I simplify this, 3 times 1 is just 3, and 3 minus 5 is -2. And -2 to the 4th power is just equal to 16, so that would be the limit. If I keep going, now I have a square root, so I have to be careful. My domain's not all real numbers. So if the value that you're approaching doesn't make, if it fits in the domain, then you can just plug it into the equation. So for this one, if I plug 0 in just to check, I get 5 times 0 squared plus 8. So this is equal to the square root of 5 times 0 squared would just be 0 plus 8 is 8. So this is equal to the square root of 8, which is 2 root 2. That means that this would be my solution, and because 0 was in the domain, I didn't have to worry about doing something else in order to find the limit. For the next one, now we have the limit as x approaches -1 for this function. Remember, when you have a rational exponent, which means a fraction exponent, you can really rewrite that as a radical. So this is the limit as x approaches -1 for the function 5x cubed minus x plus 3. This would be all to the 4th power, and this is cubed. Now, for this, if I plug -1 into the function that I have right here, well, -1, if you plug it in, doesn't make it a negative underneath the radical here, so it's okay for us to just go ahead and plug it into the function. So this would be equal to the cube root of 5 times negative 1 cubed minus negative 1 plus 3, and this is all to the fourth power, which would be equal to a value of 1 is what I got. And if we keep going, now we have a rational function. So this is the one that we already did. So make sure you just have that answer written down. Here's another rational function. So for this rational function that we have, if I plug 2 into this equation, I'm going to plug it into the denominator to see if it makes it 0. If it does, then I need to do something different. So let's go ahead and just plug that right into our calculator. We have 2 to the fourth power minus 2 times 2 to the third power plus 2 minus 2. Whoops. These new calculators always mess me up. So when I did that, notice I get 0. So if I get 0, that means I need to do something else in order to find this limit, such as maybe factoring probably would help. If you have 4 terms, remember we learned how to factor by grouping. So if you group the first 2 terms and the last 2 terms for both the numerator and denominator, you can factor out your greatest common factor. In my numerator, I can factor out, so we're doing the limit as x approaches 2. We're going to factor out an x squared in the numerator, so this would be x squared, and then times x minus 2, and in my other parentheses I can factor out a 2, or actually a 4, that would become x minus 2. And in my denominator I can factor out an x cubed, so this would be x cubed times x minus 2, and then this would be plus, and I can't factor anything out except for 1 from the second set of parentheses. And if I keep going, we get the limit as x approaches 2, and then this becomes x squared plus 4 times x minus 2 over x cubed plus 1 times x minus 2. We just did factor by grouping. Now for this, these two terms would cancel out. So the limit as x approaches 2, we can just do x squared plus 4 over x cubed plus 1. And now if you plug 2 into the denominator here, it doesn't make it 0, so that means I can just plug 2 into my equation to find the limit. So when I do that, I get 2 squared plus 4 over 2 cubed plus 1. 2 squared is 4, and 4 plus 4 is 8, over 2 cubed is 8 plus 1 gives me 9, so 8/9 would be my solution. And then I can check my answer by plugging this into my calculator and looking as we're approaching an x value from the right and the left of 2, is this value approaching 8/9? And yes, it would be. Okay, now this is another problem that we're going to look at. This is one is a little bit harder, so we're just going to do one example. For this problem, we have the square roots in our problem, and we also have a variable in the denominator, which is 0. And notice that we're trying to find the limit as x approaches 0. If I plug 0 into this equation, it makes my denominator equal to 0, so I can't just do that. Some algebra techniques that we can do here is, remember we learned how to multiply by the conjugate to rationalize our denominator or numerator. In this case, I'm going to rationalize the numerator because I want to get rid of that x in my denominator. So how do I rationalize the numerator? Again, multiplying by the conjugate, which means you change the sign of the second term only. And what you do in the numerator, you also have to do in the denominator. So this is going to be using a bunch of algebra skills. So when I do that, I'm really finding the limit as x approaches 0. So I'd take this times this term here, which would just give me 2 minus x, because the radical would end up going away because you're squaring it. And then you have this times this term, which becomes plus the square root of, you're doing 2 times 2 minus x underneath the radical, so that would be 4 minus 2x, and then this times this term would be minus the same thing, root 4 plus 2x, and then this term times this term would give me minus root 2 times root 2 is just 2. because the radicals would cancel out. And in my denominator, I have x, and I'm not even going to distribute. I'm just going to do x times root 2 minus x plus root 2. And conjugates, remember, cancel out your radical terms. So this and this cancel out, which should happen. So if we simplify again, we have the limit as x approaches 0 for 2 minus x minus 2 over x times the square root of 2 minus x plus root 2. And then I can simplify the numerator even further by taking away that 2 minus 2, which becomes equal to 0. So I just have the limit as x approaches 0 for the function of negative x over x times root 2 minus x plus root 2. Notice when I did that, now I have this x being multiplied by that whole term, and this x up here is by itself, so I can cancel those two x values out. And when I do that, I get the limit as x approaches 0, and this would be for negative 1 over the square root of, oops, made that square root too big. And now if I plug 0 into my denominator, 2 minus 0 is root 2, and root 2 plus root 2 does not make my denominator 0, so that means I can just go ahead and solve this by now plugging in 0 into my equation. So we just use the limit theorem. So when I plug 0 into my equation, I have negative 1 over the square root of 2 minus 0. And really, whenever I'm doing this, I should write the limit as x approaches 0 each time, but I'm going to skip doing that part. So plus root 2. Now for this, I get 1 over root 2 plus root 2. And if you remember, these are like radicals. When you have like radicals, you don't change the number underneath, but you add the numbers in front. So we have, and that's negative 1 over root 2 root 2. And we are still not done because we can still use some more algebra. We don't like to have radicals in our denominator. So I can simplify this by rationalizing the denominator. And that means I would multiply by the magic 1, which is root 2 over root 2. And when I do that, I get negative root 2 in my numerator. This times this right here would give you 2. So then we have this 2 and this 2 to multiply together, which is 4. So negative root 2 over 4 would be my solution. And a good way to check your answer again would be to plug this into your calculator, look as it's approaching the left side and the right side, what is our value as we approach 0 going to be, our y value I should say. Now for these tend to be the hardest and most difficult problems, the one with the radicals, and so we're going to be doing a lot of this kind of practice in class. So just bring this with you, and again, like I said, we'll do more of this in class.